Arni Rao from Medical College of Georgia and director for the Lab for Theory and Mathematical Modeling, and also from University of Augusta, Georgia. He's also serving as the Senate affiliate for the Faculty Development Committee of the Senate. And we are pleased to have him and really appreciate his time, taking time out of his vacation. And he will be presenting multi-level contours within complex plane bundles. Over to you, Professor Rao.
Okay. Hello, everyone. And thanks a lot, Professor Bashir. I'm really honored for this invitation. And I want to thank you and LUMS, Professor Anwar, everyone involved in this seminar series. So when I received this invitation, last year itself, in fact, John Conway name is well known. And initially, when I received, I thought to the recent work, what I have done. I have been working on very busy for COVID the last 2 years. But when I received this invitation in the name of John H. Conway from Professor Bashir, then I thought to present on my recent works related to the complex plane bundles. And this talk, this is a lengthy, very lengthy article I published last year at about 75 pages. And so I would request Professor Bashir, please stop me. Please alert me when I finish 45 minutes so that I can, rest of the time I can quickly conclude. But until then, I would go with ease. I want to explain the things very detailed. So please alert me. Once again, I want to thank you for the invitation and looking forward for my talk. So let me start my slides now. So as you see the title of the talk, multi-level contours within complex plane bundles. And I want to dedicate this talk to my close collaborator and friend, Stephen G. Kranz. He's a professor who completed 70 years. So he's my collaborator. We have been collaborating on the COVID for the last 2 years. We published several articles. And happy birthday, Steve. And he is a very well-known complex analyst. And this work really fits for his birthday. But the presentation of my work, whatever I'm presenting today, is not my collaboration with him. This particular presentation, what I am is based on my own work. But last couple of slides I will share based on my collaboration with Steve.
Professor Arni, this is the same Stephen Crott, जिन्होंने वो book लिखी है.
हाँ वही correct. उनका जो किताब popular है.
Very popular book. Yeah.
हाँ, so हम दोनों collaborate करते हैं.
That's wonderful.
तो नीचे लिखा है कि intensive collaborative work on COVID modeling. तो हम दोनों Springer का एक publication भी उसमें निकाला. तो कैसे Springer ने invited us कि how did you collaborate, and we published about 25 articles.
Yes, Mohammad Shahzad, what is your question? You can drop the question. Okay, for the audience, you can drop the question in the chat box. We will take on all those questions time to time.
अच्छा अनवर भाई, आप मुझे 45 मिनट के बाद थोड़ा अलर्ट कर दीजिए.
Okay. Continue.
Thank you. Yeah. So this is what I'm trying to I want to dedicate this talk to him. In fact, next year I'm organizing a very big event, 2023 spring, two-day event on complex analysis. Yeah, outline of my talk. First, I will describe on the basics of the contour formation on a complex plane, and then I will touch on what kind of bundles I consider in this talk, and then the role of randomness. And this is what the originality of the work I have done. I brought the randomness concepts into the complex plane, and then I use that concept to understand how the contours of one plane travel to the other planes, other complex planes. That's what the new term I phrased. That's a multi-level contours. That also I'm going to explain through this talk. And then I will describe holes and islands within the bundles and their applications. And I would love to have as many questions as possible during the talk or after the talk, end of the talk. So most of the things what I'm going to explain is available online based on a recent article, 2021, I released in archive, and that will appear in the 2022 in the next few months in the Geometry and Statistics by Elsevier. Let us consider bundles, composition bundle of this sort, where these are there are several planes are there. I think 1, 2, 3, 4, 8 planes are there, intersecting each other. And then see here, I have drawn contour. This I call multi-level contour. See each one plane to another plane, they travel. Z1, Z2, Z3, they are all complex numbers on these planes. And then then we have multiple, the several, for example, I drawn arbitrarily 3 contours. So I called M1, M2, M3. And you see that Z1, Z2, they're all, belong to the Z1 belongs to C1 only. Here Z1. And then Z2 belongs to C1, C2, Z3, C2, C3, C6, and so on. Sorry. So this is a trailer. So my rest of my talk is about how do they travel from one plane to other plane. That's about the rest of the talk, and their various properties of that kind of contour. So as a snapshot, I just showed up front. This is what this is going to happen because of the randomness and also non-randomness also. That travel with the contours traveling from one plane to another plane. So gamma I mi indicates the piecewise arc. If I be the the M1 gamma I M1, not mi, that is the first arc. I mean first multi-level I showed 3 contours, multi-level contours, M1, M2, M3. So let gamma I M1 be the ith piecewise arc out of 7 arcs. There are 7 arcs. You see the M1 was constructed using 7 arcs. So let Ti be the Zi tau with alpha 1i with the tau range between alpha 1i, beta 1i for I equal to 1 to 7 with the parametric representation or a real valued function of function Zi mapping alpha 1i, beta I onto A1i, B1i. So this is from the real line. This value from the real line. Then the alpha 1i, beta I for the tau after the transformation. So Z T1 is a complex number for A1i, T1, A1i less than or equal to T1. I mean, T1 lies between A1i, B1i, this one, T1. They are real numbers as I mentioned. Then the length of the contour M1 can be computed using the sum of the 7 integrals. Where thus it will be made up of 7 piecewise arcs. Similarly, the contour M2 also can be constructed with the sum of 4 integrals, M3 sum of 4, because M3, M2 as we saw in that other figure, it is made up of 4 pieces, and M3 also made up of 4 pieces, 4 piecewise arcs. Where here phi I and psi are corresponding parametric representations. As you saw there, psi I, here phi I and psi, just different symbols. Now, given that the contour formation, the basics on that, so let me introduce infinitely many bundles of this article of how did I consider infinitely many bundles. So I considered bundle of this sort where they know the infinitely many complex planes arranged like that. And let us consider an orthogonal plane C0, I call, that could be anywhere. Arbitrarily I considered that location, so it could be anywhere, one of these or any other location, which is orthogonal to the bundle BRC. So BRC stands for the bundle and C0, this orthogonal plane. Now the first theorem, the very first theorem of the article, that is the shortest possible multi-level contour passing through the bundle just as shown is the real line. I'm not proving this on proof can be seen. So the idea is, if you consider this bundle, the shortest possible multi-level contour passing through all these planes is a real line.
Excuse me.
Yes.
Professor Arni, what do you mean by shortest possible multi-level contour?
I mean, without any, there is no curvature.
Oh, okay.
There is no curvature.
And what does it mean by multi-level?
Because it's passing through the several planes.
Okay.
Several planes, crossing one plane to other plane. So in general, complex plane, these numbers don't cross the function. If you formulate a function, that is still lies on that plane only. Complex plane, it doesn't cross it. However, maybe the value. But then because of the property I'm going to introduce, that crosses the plane and then connects between such way the joints. So shortest possible with multi-level contour, as I showed, one plane to other plane to the contour, piecewise contours, as I just demonstrated. Real line. So complete proof can be seen in this article available. So there are many things are there. I'm going to, so this is one of the elementary, first elementary results. So I'm skipping the proof, but one can see there. Then the interesting thing comes is how when you spin it. So I'm going to explain the proof of that, the spinning of the bundle theorem. So when we suppose BRC is rotated, the same bundle what we shown. That's a good question, by the way, that Anwar asked it. That's a good question, because how do we see that, the shortest possible means what? I like that question, because we need to understand that means without curvature. So suppose the bundle BRC is rotated counterclockwise, such that the line passing through 0, 0 of the plane, of all the planes, origin within the BRC forms an angle theta with the y-axis. So the y-axis is there, imaginary, and then if you counterclockwise, anti-clockwise, we just rotate the bundle, and the rotation is continued for all the values of theta 0 to 360 degrees. Then the space created due to the rotation forms a 1-1 correspondence with BRC. The space created due to such rotation, rotating that from 0 to 360 degrees, that forms the space due to that rotation forms a 1-1 correspondence. Let us see the idea of the proof. Suppose we make the same, let us take the bundle BRC and combined with, let us combine that with the positioning of the C0, whatever we initial bundle, and we take the position of the C0 and place it on the same bundle. So now what, once we place the same thing, that means two bundles are exactly occupy the same space. Now let us call B R the superscript 0 or O for the original bundle, or BR C for the copied bundle, BRC, that for the C stands for copied bundle. And suppose we tilt BRC as follows. Use a little bit tilt counterclockwise, BRC to the left side, counterclockwise, such that BRC, the copied inclined at a copied bundle, this copied bundle inclined at an angle theta with the y-axis. Now let us consider the arbitrary plane. Some plane, let's call CP in the original bundle, BROC. The same CP will be there because that is copied, same CP will be there in the tilted bundle also. Tilted and copied bundle with an angle theta. So call the tilted and copied, let us call here BRC, that BRC comma theta. The difference between that is BRC is before tilting, BRC comma theta is tilted the bundle at an angle theta. Same bundle, I called it BRC comma theta angle. So now CP, the arbitrarily chosen plane CP in the copied bundle also intersects with infinitely many uncountable planes of BRO, original bundle. So by first theorem says that, that one can draw a contour that passes through all the infinite planes. So there is no point of, because of that theorem, there is no point of CP that does not intersect with the points of the bundle. Any point we pick up in the CP on the tilted bundle, that intersects with the points of the bundle.
Excuse me, Professor Arni. What is the analytic definition of this BRC0 and BRC original one and the copied one? So are you? Can you show the equations of the contour?
Yes, we'll go to the equations of the contour.
Okay. So these are some specific kind of contours, right?
Yes, I mean the regular contour, but they are piecewise contour. So each piece, ith piece, there are 4 pieces are there. After transformation, this is how the integral length of the contours are we construct in the complex plane. And then these are the the phi and phi I and xi are the parameter representation because from the real line, from the real values a comma b, the function is mapped to the complex plane, and then the plane to the, as we regularly compute the contour on the plane. So contour integral, yeah.
And what is this z and phi?
Z is complex, when we take the derivative z of t1. Z of t1 is a complex number within the area a1i t1, the z of t1.
Okay.
Function. Yeah, that function that after transformation, so the z prime is a derivative of that. So zi, this z, z, and this is psi I is the parameter representation for the first parameter. Once a parameter representation, when we do that, that's how the way, I mean, the regular contour construction, that's a length. This becomes a length integral alpha 1i to beta 1. This becomes length of the integral for the ith piece. So each piece we sum up. Thank you.
Thank you. Thank you very much.
No, you're welcome. That's a good point. Yeah, because we need to understand how we construct the contours. Then, so this is then we tilted. This is the tilted. Same thing we copied the tilted, and after tilting, so no point of CP. Well, after tilting the arbitrary plane, the CP, same CP, the values are there in the original bundle. But after tilting, still the same CP there, but now the CP, earlier CP doesn't intersect with the other bundle, other planes in the original bundle. But this after tilting, this CP intersects with all the planes of the bundle. So no point of CP that does not intersect with the points of the bundle. So we have, since CP that belongs to the copied bundle, CP belongs to the copied bundle at an angle theta for some value 0 to 360 degrees. That implies CP belongs to BR original bundle also, the CP also there. So this means for every Z belongs to CP, that implies Z belongs to BRO. So since theta is arbitrary, the statement 2 is true for each theta. Hence, that is proved. That means the space, the 1 corresponds with the space. Because it's for arbitrary, theta is arbitrary, CP is also arbitrary. This is true for the entire space, 1 corresponds with the original bundle. Now let us see on the multi-level contour. The same thing with the previous slide was on the previous setup was on the without any randomness. Now let us see how the random environment plays a role. So what we do, we again pick up some arbitrary plane, is a CP or CL from BRC, again from the bundle, same bundle. So this bundle has a BRC again. The BRC consists of the infinitely many parallel complex planes which don't intersect with each other. Then they are all, there is orthogonal plane C0 that intersects with the BRC. So now let us denote random variable. This is a real valued. I mean, in the general, it's a real valued function, but here describing the position of the so this describes the position of the contour, because this becomes now a complex valued function. X of gamma L CL. That's we introduced that random variable. Gamma L is the contour, I call contour drawn from the CL. CL stands for the L, some number, not L, not be just L. CL stands for the plane within a bundle. And then gamma L stands for the contour drawn from the plane CL that has originated in the plane. So we pick up some random number, and then that's a complex number. Randomly pick a complex number. Again, is ZLT, the real number T0 with all the value generated, the contour generated by Z of T0, and then so initial value Z of T0, and then how do we generate? Let us see. Suppose initial value is picked arbitrarily, initial value ZL0, initial value on the plane CL. We pick arbitrarily initial value. Let us call that X of ZL0 CL. CL stands for again on the plane. So that value, once you pick up, then we form a contour. We formulate a contour. I will explain that in the coming up slides. So that contour X of ZL TCL, that actually for T0 to infinity with various values picked up randomly, that I will explain that. And the ZL belongs to CL is a stochastic process because of the different things, different collection of random variables. These random variables all are now complex numbers. Collection of that forms a stochastic process, because that will have a two-step randomness that I'm going to introduce. First step, we pick up a random number, that is a complex number here, arbitrarily, first value, and we draw a disk, as we will show. So what we'll do is we draw a disk. Once we pick the number, initial value, we draw a disk with a radius R0. Second step. First step is pick a number, and then we pick R0, the radius around the initial value, and then draw a disk. So initial value is picked arbitrarily, then the drawing of this disk is random. So radius is randomly generated, and we draw a disk, and then inside that we pick up a number again randomly. So the radius of the disk is, prior to the picking up, we don't know. Only ZL0 is known. That means the value is known after arbitrarily picking. So the two-step randomness is involved. First step, you pick a number, draw a disk. Again, within the disk, you pick a number, again draw a disk around that. So each time, first time you call R0 and then R1 and so on. Two-step randomness. So they're infinitely, similarly, we can draw infinitely many options around, because within the disk, you see that within the disk, there are infinitely many options to pick another next random number. That's a complex number there. So infinitely many options are there. Yes, please.
Can you a little bit elaborate what is that intersection of CL in the previous slide? Yeah, intersection CL with CO.
Yeah.
That is that.
So that I'm coming up now. That is the next slide coming up. Yes. So C0 intersection. Yeah, this is a good question actually. What happens is these disks, keep on expanding. This we can move. Our R0 may be so small. Maybe R0 may be so big. We saw randomly pick it up a radius. So initial value when you pick up, this C0 is already there. You saw in the bundle intersects that line in the bundle. So this is a one plane. I just, as a cross section, I took one plane. I called CL. but there is this is part of a bigger bundle. Now CL means this intersection of CL intersection C0 means the value this disk might touch this intersection. This is the intersection of all the which intersects with all other planes.
And how this trajectory of the red line, where the points are randomly chosen, so this red line can be anywhere, right?
Yeah, really is contour. Yeah. Anyway, so I just showed an example line. It could be.
Yeah.
Yeah. Good.
Yeah. Thank you. Thank you.
Yeah, that's a good point. In fact, how that moves. So that could be, as we see, as we evolve, that we'll see that this red line could be always lingering within the same plane, or it might cross the plane. When it crosses the plane, it becomes a multi-level. It doesn't cross, it becomes an ordinary contour. Good point. So let P be the probability that the random variable x of ZL CL initial value has transition from during this period T0 to T1, the time interval. That means first value, initial value to first value, the probability of jumping from one value ZL0 to ZL1. So ZL0 initial value. So X of this is initially given that it jumps to ZL1, that is probability ZL0 to ZL1. During the, so all such probabilities can be computed. So one probability is that probability ZL0 to ZL1. All such probabilities can be computed. Because there is one such probability, if you integrate all such possibilities of, that can random, that next complex number could be anywhere within the disk. So summing up all the probability, that will be integral of all the disk is open. So summing up all the probabilities, that will be P ZL0 ZLT dt equal to 1. All the possibilities of picking ZL1. It could be anywhere within the disk. So within the time interval, the somehow integral of all the probabilities will be 1. Now we'll see that, I'm going to define again the C0 intersection CL. Now the Markov property, that is being so a contour formed by the set of points generated by X of ZLT, CL on the CL, that what we just saw within the bundle intersecting C0 and satisfying the distinct complex number property. So distinct complex number means you saw that based on the initial value of whatever the initial value the random variable picks, the disk is found for that especially for that with a specific radius. So the initial value and the two-step initial value and the second step. So this forms that makes that particular property makes it a distinct, the complex and distinct. So this entire process that obeys continuous time Markov property. That means the time is continuously, the picking of the new random numbers is continuously happening, but it picks only it depends only on the previous disk. That's why it is a continuous time Markov process. So for the understanding that, let us see the behavior of the X of ZLT around the intersection, what you asked that one more just now. So let us see the behavior of the contour at the intersection. So again, CL intersection C0 means C0 is already orthogonal, that is orthogonal plane to the bundle, and CL is an arbitrary picked bundle. Let us see the behavior of that. This particular behavior is essential for our understanding of the multi-level contour. So whenever X of ZLT, CL reaches a point, ZLA, some number arbitrarily again in the set, CL intersection C0, then at that intersection, there are two options are there. As we saw in that figure, the two options are there. Let me go back, for clarity. Yeah. So ZL, whenever it intersects here, after reaching, it could take finitely many steps, infinitely many steps, reaching somehow the contour reaches here. It will have two options. Either from here, the new disk is formed again on the, which completely on the CL, or the new disk could be formed on the plane C0. C0 is perpendicular, C0 that lies on the line. So disk could be formed on the line itself, I mean on the plane perpendicular or orthogonal to the bundle, or that contour can continue the disk on, because we don't know in advance, based on the two-step randomness property and the formation of the disk. That's what this is, that statement. I'm going to explain that there. So it is that. So the next number, the set CL intersection C0 or within the plane C0. That is, as soon as X of ZLT CL chooses a number ZLA, it could be countable number of transitions, then the two-step randomness will help to disk either that disk, namely on the D of ZLA RA or D of ZLA RA C0. That means this new disk could be on the plane C0 orthogonal to the bundle, or on the CL, as I just explained using the figure. That means D of this could be subset of CL, or D of the disk subset of C0, wherever it is, depending on if it is here or there. So the next number, ZB, could fall within the disk such that it is on the line. If it is on the C0, that will be on the line. Alternatively, Z of LB could fall within the disk such that this is on the line by intersection of line formed by intersection of CL intersection C0. So that means these, either one of that CL intersection these. So these two are defined as follows: CL intersection C0 complement equal to, for all the complex numbers on the plane CL, and they don't belong to the intersection, or they belong to the intersection, they belong to the plane C0 and does not belong to the intersection. That means the disk could be on the C0 or on the CL, the formation. So from the randomness, two-step randomness, the contour starts, disk formation, again contour, again another step. It might take so many steps, infinitely many steps or finitely many steps. We don't know, because it's a random process. After some time, it hits the line C0 intersection CL. After that, once it hits the line, it could escape to the other plane, or it could remain in the same plane. So that property is essential for, so if CL is the plane, so that we see that it could, some of the contours could remain in the CL plane forever, or when it reaches the C0, it could move to, possibility to move to other plane. The contour can be formed in move to other plane. So this is a very important property, the two-step randomness property.
Excuse me,
Yes.
how we can see the complementary part? So by complementary, we mean everything which is outside and inside, right?
Correct.
Yeah.
Outside, inside. So the two
Outside.
possible, yeah, outside means either leaving the plane and going to other plane, or remain in the same plane.
Mhm.
That won't cross the bundle anyway. It will be within the bundle. Whether the contour will stay in the same plane or will cross the one plane to other plane, other complex plane. I mean.
Yeah. Thank you.
Good point. So that's what we saw in the previous slide. Once it hits this, see, this intersection again, C0 intersection CL, this piece here, C0 intersection CL. This is C0 intersection CP, C0 intersection CQ. So only through the intersection, once the contour reaches here, it might cross it again, go there, come back and go, leave to escape to new plane, or come back to again this side, or might oscillate in this area. All possibilities are there, or might, depending on the disk, the formation of the disk. Symbolically, it can happen anywhere. Any one of the contours shown in this figure. So then now the ZLB, once it is formed, the multi-level contour, we see that if it is, as I just explained, and as I explained, if it crosses the plane it will form multi-level contour. If it doesn't cross, it remains form a regular contour on the CL itself. So using multi-level contour on CL, C0, and then moves or remain there. That's what I explained here. So the ZB depending on, so ZLA to ZLB, that is the crucial, that piecewise arc, that is crucial to see whether a multi-level contour is forming or not forming. Now again, if we consider the same bundle and then make a, if it takes infinitely many intervals to reach. Sorry, let me explain the statement. So if we consider the same bundle and then the infinitely many intervals to reach from ZLA, the contour from initial value to the ZLA, infinitely many disks of formation, all that done, then the intersection of all the disks is non-empty. Suppose the initial value as earlier, you consider the initial value and then let's call it ZL0. So let D be the disk out of two-step randomness, as we just explained. So there are about 30 theorems are there in that article, about 75 pages. But I'm not going to explain everything, but then the foundation ideas I'm going to explain here. Rest all one can follow, easily follow. Once the foundations are, those things, assumptions, everything I'm explaining, everything is written very clearly there. But those things I'm touching, which are crucial for that to follow rest of the article. So again, you see that intersection here, once the disk formed, all the values of, even there are infinitely many disks are there, still there are initial value, still there is a point randomly need to be picked up. That's why the intersection would be never empty. Let us see how. So R1 be the generated randomly. So this first value, initial value picked up, first value such that D of ZL1, R1 subset of original disk. Similarly, further Ri is generated, ith value is generated randomly such that the disk is subset of the ZLi-1 or Ri-1. So ith randomly picked value belongs to the previous disk formation due to the L-ith, the disk due to the formation of disk from the disk formed based on this ZLi value with a radius, two-step initial value picked, the previous value picked and the randomly generated radius. So idea only, the intersection is, that means that's why the idea of the proof is because of this property here. The intersection would be D of ZLi, Ri will be non-empty. As I mentioned, there many things are there. So this is another interesting theorem. So there exists a unique contour. So now how contour formations are done, that we saw, whether multi-level contour or regular contour. Now the property, if you see that if there exists a unique contour gamma L for each initial number chosen in the bundle combined with C0, and that the contour intersects with the bundle and satisfies the distinct complex numbers. So whenever these property hold, there exists a unique contour gamma L. The contour formed under the setup, whatever I discussed so far, that's unique. Yes, please.
What do you mean by distinct complex number property?
Distinct, yeah, good point. That distinct complex number means here the previously we saw that you pick a number R0 and then you pick R1 again, R1, then R2, R3. So if there is a possibility that within the disk again randomly same complex number could be picked, but that is avoided there.
Okay.
That's what distinct means. The same complex number is, once it is picked, it is being blocked.
Okay. Thank you.
Yeah, good point. Thank you. Now I'm not giving again proof for that. One can read that. One can read in the article. But main idea conveyed. So you are all clear what I'm explaining anyway. So now space. Let us understand because this understanding of space, then that will lead to the whole, how the whole is created and the islands are created. So space created by two complex random variables. Let us see that. So gamma L, now we saw the contour formation, and then with random number generates this contour, and y, let x and y be the two complex random variables. For t greater than t0, t greater than t0, with initial values are given. So this is a random variable. So this generates gamma Lx, this piece generates gamma Ly. Both are on the L stands on the, this is a complex plane, Lth complex plane CL. This is from the CL. That's why I put the L there. Y means the random variable Y. X means random variable X. So two spaces, I mean, each contour, this is two are distinct. Just now the theorem is a unique. Gamma Lx is unique. Gamma Ly is unique. So that creates two processes. And then I call that, the two, because stochastic process will have a state space. That means the space on which the random variable hops. It jumps from one place to one state to other state. So that forms a two state spaces. So ALY, AXCL, AYCL are the two complex two state spaces on the contour, the contour, that the space formed, because it's a stochastic process that we call state space instead of ordinary. We can call it space also, not a problem, but it's called a state space because there are states are there. The random variable hops from one state to another state. So one is AXCL, one another AY. So these the values are Z such that initial value started and then all other values the same, the space. We discussed this many times during the talk. The symbol is AXCL stands for the space created by the gamma Lx. AYCL stands for the space created by the gamma Ly. Now another theorem, that is the two state spaces AXCL and AIC are identical. The spaces may be identical, but the contours need not be identical.
By identical, you mean?
They mean they are exactly same.
Yeah.
The space.
Yeah. Some isomorphism or something?
Yes. Identical here means they know the exact one-to-one correspondence. They exactly same values they occupy.
Okay.
But the contours need not be identical. Contour can be hopping from one. They have a different shape, but they may be touching the same points on the space. But the contour might come from some other location. They might come back to that.
Okay. Thank you.
Thank you. Good point. So the difference between the spaces are identical doesn't mean that the contours are identical. Now the removal process. Now once the space formed, we will remove them. The space, once the space of the contour formed from the bundle, we will remove them. So the gamma Lx be the space because of the random variable x. Now I call the gamma Lxt C be the space of all the points minus the contour. So gamma Lxt defined as BRC minus gamma LT, the set of points which are not BRC, and then you remove them. So BRC, and then from the bundle you remove this space formed due to the gamma Lxt. So the timing between the introduction, so once the initial value is here introduced, and after some time removal. So removal also simultaneously starts happening after some time that I will discuss after certain time T1 or some TC, some arbitrary time, that removal process starts. And then once the removal process starts, the space also keep on happening. The contour formation also infinitely, continuously happening. At the same time, after some time, the contour data is being removed from the bundle. So that removal process. So there is a loss of space created by that loss of space created during the interval. So first let us TD1 be the time where introduce this removal process. The initial value when the contour formation, and then that contour keep on forming after TD1, but we start removing them. So that can be expressed using a differential equation, BRC. So removal at a rate phi 1 x gamma L xt. So the gamma L xt, that removal rate, removal from that within that interval, this kind of, so BRC by dt, this part differential equation to explain the loss of space. Similarly for all the other intervals. Now the second piece, first piece we removed, second piece TD2 minus TD1 such that means equal interval. See the TD1, this is removal time minus the first removal time, then the removal time and the origin of the contour. That means jump. This is jump time between the removal. So jump process. This one jumping process, jump process, and then the time between the two removal processes are same identity. That's the one under the. That means we are uniformly we are removing the timings are uniform. At uniform time intervals we are removing the bundle formation. So that the equation at the TD1, the initial value, and then the second step removal process. So second step removal, first is phi 1x for the interval T0 to TD1, and second interval TD1 to TD2, and so on. Suppose TD1 is the previous construction randomly chosen, and the rest of the future time intervals are fixed to maintain the interval length equal to TD1 minus T0. That our time intervals have constant length, but the piecewise contour lengths in these intervals need not be identical. That means the timing, that's an important point here to notice, that the timing intervals are same, but within an interval, the contour lengths need not be same. As we just saw, the contour formation is based on the random process. So the length of the interval, length of the contour depend on the wherever the two-step randomness within the disk. You saw that. So although the time intervals are same, the lengths of the contour need not be same. That's why the removal process, the removing could happen in a different scale. Removing of the contours within a bundle could happen in a different scale. Formation could happen. So pictorially, if you see that these two pieces of the same contour, the gamma L is same contour, but after it going somewhere else and coming back, so the same contour, initial value, once the initial within the disk. So this space we cannot reach the shaded line, because this space of this is the disk, and this contour blocks it. So this disk is formed, initial value. This space is lost. That means the lost means this space is not available for formation of the contour due to the removal process. Now because of this property, a new concept will be emerged within the bundle that we call hole and island. For example, I'll define, before defining, just a motivation. So this is again, quick recap. This is a bundle. This is the thing we considered because of the formation of the contours from initial value. So somewhere it is there. So there are bundles below some line. So once we remove this, because of removal process, these two, the bundle became, there is a hole between the two. Within a bundle there is a big hole. Because of that, the contours cannot travel anymore between the bundle if the hole forms there. So the red and blue indicate two different contours. So let us define based on that. So this kind of, these are islands are formed just because of deleted properties. So by definition, I just motivated. Before definition, just wanted to motivate you what exactly happening. Now let us see the definition of a hole. So hole H is defined as a closed set of points in the bundle such that no point of H available to be chosen by arbitrary, as I just described. This random variable ZLT for the complex plane L generated from the plane L, some arbitrarily given the name XA, originated from the CL. That particular this random number, the random variable, the set of points within the HR, the closed set of points in the HR, they are not available to be chosen anymore, as we just saw in the previous diagram, the shaded lines. That piece, that part of the disk cannot be reached. For example, if you let ZL, XL, XAT be the set of numbers of gamma L that got deleted due to removal process, then XA would not be able to choose a number. That's what that would not be able to choose a number from this thing, this within that interval. So there could be many such holes as we saw. So two or more contours using same set of points within the same period, then the removal process of one contour would delete the common set of, so that means the contour keep on forming, other contour could delete the one contour's space, so that the hole is, that means there is a possibility of creation of hole by removal process of another contour also, same contour or maybe another contour, so that the space created becomes dynamic, so that this H becomes dynamic. Similarly, island is defined as a set S subset of BRC and non-empty. The set S is called island if any element in S is available to be chosen by a random variable, but they are available, but no contour can be drawn to an element, to a point from S to outside S. That's why now, and the islands you saw that within island one can draw a contour, but the contour cannot cross the island. If that cannot cross the set, that set we call an island. So you see here this piece, this forms an island here. So ZL DXA, ZL JXB. So this is the XA value. So one contour, another contour, two contours are there. The disk is formed. This piece, this is a ZLXB, ZLJXB intersection point. And then this red line is a ZLJXC, another contour. XA, XB, XC, I called it different arbitrary contours. So one contour, another contour, the deleted. So this piece cannot be within the island. No contour can be drawn from the element. So this forms a, this is in the set, this set of elements here form a contour. Now union of collection of all the holes within the bundle is a compact. That also I'm not proving. One can see that. So, and then similarly, as I mentioned, there are more than 30 theorems are there, but essential content already explained. Suppose infinitely many random variables are there. They are introduced one by one. And if every point within island is part of a contour, then due to removal process, it becomes HTC. Yeah. Sorry, that becomes a removal process of the one contour. As I explained, the removal of the one contour could make a islands for other islands due to the intersection of the other contours and the space in between that forms an island. What are the consequences? So we learned so much on the multi-level contours. Let us see the consequences. Why do we need to understand them? What are the consequences of those things what we learned? So because of the multi-level property for the contour, the multi-level contours, the properties introduced here. Say this is a contour here. Let C1 be a plane and C2 be another plane. So this piece here, contour, because of the multi-level the intersection and then traveling property, the discussed one now traveling of escaping of the random complex number from one plane to another plane and joining those lines, joining those complex number through a contour, that can be used to share information or transport information from one plane to another plane. This is the biggest achievement, and that links to the information geometry. The properties what we just saw, they can be used to understand the properties of the information geometry using these multi-level contours. These are examples, the shapes are example, arbitrary shapes I given, these are one contour. So various shapes that can reach by through multi-level, the properties can be transformed. That's a major gain. And then
these are linear transformation or
no, the transformation
other...
through the multi-level, the same,
okay. Multi-level transformation.
Multi-level transformation. Okay. And then the bundle, within the bundle, you see that here. Yeah, various ways, this initial value, and then it can travel to various other bundles.
Yeah. Professor Arni, we are 5 minutes away from the
5 minutes. Okay. Yeah. Then, I want to sum up. What we'll do is, there are some PDEs also formed, how to understand the relative losses, one loss to other, one contour to other contour, the relative spaces loss, how we lose the relative spaces relatively, that I explained to the PDEs. And then so since I'm dedicating and this entire work to my collaborator, very renowned complex analyst, so I want to share the last 2 slides on my collaboration with him. So we actually essentially collaborated on COVID. There once this thing done, this last year, whatever I explained last year, just this year, me and Steve collaborated on the whatever our collaborations on the complex analysis, that I will explain in the 2 slides, just 2 slides. So recently we proved in the article Geometry, Information and Complex Bundles, a special form of a Jordan curve theorem. So if you consider a same complex bundle, and then this is a sphere, and this sphere, again, the points on the boundary of the sphere, on the surface of the sphere, are joined using the multi-level contours. So the special kind of there are these lines are the 3 different, any number of contours can be formed. See here, these are all the contours, different blue line, yellow line, and green line. There are contours on the surface. These dots are on the surface of the sphere. So 3 Jordan curves, J1, J2, J3 for arbitrarily. So Jordan, suppose we consider a disk, a ball within the bundle, then one can construct a Jordan curve passing through the boundary of the sphere. That's one theorem. And then we also showed that covering theorem, infinitely many, so Jordan curves on the ball that cover the union of all the Jordan curves becomes the points on the surface of the sphere. So this is these 2 just slides, summary of the slides. These are just this year 2022, the previous one whatever I explained on the last year, and these are all the references. Although the multi-level contour is newly introduced, the standard books are seen, for example, the first article is about multi-level contours explained. Then the classic textbook, Alphonse, Churchill, Kranz, Wood, all the books are there. And then after I published online, and then I come to know the work done by Wu and Yao through my collaborator. I come to know about their work, and then they consider different kind of complex bundles, and then they done a lot of fundamental things on the Yao and Wu from 70s, and you see that in circles bundles they considered 77. These I didn't know this work prior to me doing this, so I would like to now see that the association between this work and the other works, the Chern and then Wu. Yeah, they done a lot of work on this kind of, the complex plane bundles, circle bundles and the vector bundles connection. Yeah,
Yeah. Wonderful.
Thank
Wonderful.
you. Thanks a lot for your attention.
Thank you. Thank you very much, Professor Arni. That's wonderful to listen to your work with Stephen Krantz and such a quality of references and such a quality of results. And definitely, it was highly technical, but you made it very elaborative. So let's have some question. Anyone
Sure.
have some question from the audience? I
Is my
kept on
slides are
asking the question.
sharing or my slides no more
Now your
sharing?
screen, now your
Oh,
screen is visible.
okay.
Now we can see you. So any question from the audience side about this topic and these explanation? Probably someone, Waqas? Okay, let me just add one more thing. Professor Arni, because you are a statistician, right? And you are working in geometry, complex geometry, I would say. So what is the interest of introducing the randomness here and when you were constructing the contours? So what was the major motivation behind this particular randomizing thing?
Correct. That's a good question. The motivation.
Yeah.
I see. I have last year, the year before, I mean, I taught complex analysis course for the advanced graduates and the undergrad, various things. I taught differential equations, complex analysis. So always the dynamical systems, that's been one of my interests. Also, I want to thank the brilliant students I taught and my teachers, my friends. Various discussions, we have been discussing the practical value. I have always wondered about practically where we can use. So one of the things, I'm going to apply these multi-level contours is on the climate. It looks very, very odd. There is no climate component in the analysis, but now I applied for another grant also to study the climate using this type of like transportation of information from one. So I see that the climate can be studied, not just climate of the earth is not dependent only on the climate, only on the situations what we create on the earth, but it is also related to the climate of the universe. So that's the hypothesis I'm working. That actually then that's one of the motivation. Another thing is the information geometry. Last year, I published a book, edited a book on information geometry. Myself and Angelo Plastino and S.R. Rao together, all three we published a book titled Information Geometry. And also myself and Steve also we worked on virtual tourism, and then how the various important tourist location in the world that could not be one cannot visit due to the COVID. How the VR technology with the conformal mapping, how close we can bring it to the visualization with respect to the real world. I mean reality with the instant with what's called it's time sensitive, like the same time the various, if you can see in the YouTube, you can see various online videos also, but then that may not be time sensitive because they are sometime back recorded. You don't feel the climatic situations, you may so to incorporate the time sensitivity also without a conformal mapping along with information geometry. So a lot of in my back of my mind, information geometry is going very this thing. And then luckily I taught this, this complex analysis was, I taught with them before several
And
times.
may you shed a little bit more light on information geometry?
Yes, information geometry, that classical article where we all know as the Rao-Blackwellization theorem or Cramer-Rao inequality. Information geometry is 1945, that famous article then by C.R. Rao, very famous statistician who celebrated his centenary in 2020. Shaina knows all of that because he also visited Professor C.R. Rao long ago, visited University of Guelph by invitation from Dr. Khan that time in his 80th birthday. So he is well known. He introduced the information geometry in 1945. The idea is using the geodesics and the Riemannian surfaces how to measure the distance between the two populations. Populations means, the two different populations which are having different characteristics. If you want to compare the mean of two different populations, just compare the mean. I mean, the height of one population, height of the another population. What we do, we take the average height to compare. But if the population have many characteristics, how to compare? That was in 1945, the article that became very famous, and the information geometry was introduced. Then later, especially that was advanced to next level by Arni S.R and also by the Amari, Shichin Amari.
Habib Amari.
No, Shichin Amari. So S.I. Amari.
Okay.
So Shichin Amari took it to the very higher level. So the Amari distances is we call. So information geometry became a very one of the major areas that has a physics application. So my collaborator last year, Angelo Plastino, was a physicist that book release. So
that's wonderful. That's wonderful. With your virtue, we came to aware about so wonderful areas. Once again, thank you very much, Professor Rao, and we wish you all the very best for the success of your project. And maybe some other time with some new research in the same John Conway series. Thank you very much. That's wonderful talk.
Thanks a lot. Thanks a lot,
and
Professor.
now I need to just advertise our upcoming seminar, which is in the next week. This is a kind of tradition we have. So our next seminar is by Professor Bernard Schrumpfels, who is currently associated with MPI Max Planck Institute in Germany. And moreover, he has an association with UC Berkeley at US. And 28th March is a special day. It is the 60th birthday. So I didn't know that today is you dedicated it to Stephen Grant's 70th birthday. And next week we will be celebrating the 60th birthday of Schrumpfels, and he will be turning to 60. That's wonderful.
Happy birthday to him also. My best wishes.
Yeah, so, and thank you very much for introducing Stephen Grant's here. I was completely. We are really honored to have a talk on the work of Stephen Grant's, and definitely through your seminar. And this is our next week's seminar, and where some new connections of linear PDEs developed with algebraic geometry. So this is his recent work on the connection of algebraic geometry, how algebraic geometry connect with linear PDEs. Wow. So he is going to explain all these things in the next week. So that's just the advertisement of the next seminar. So thank you, Professor Rao. Thank you very much.
Yeah, I want to thank you and Shahina, and wish you good luck all, and look forward to meet all of you again some other occasion and the conferences or here. And let's keep in touch.
Yeah, thank you, Professor.
Thank you.
Thank you.
Thanks a lot, Shahina.
Thank you.
Yeah.
Bye. Thank you, everyone. Bye bye. Take care.
Bye bye.